Hello everyone, this is Shufei Zhu from Penn State. Welcome to my talk. In this talk, I will present our work measuring and modeling the label dynamics of online anti-malware engines. This is a joint work with colleagues in my group and researchers from Illinois. Security researchers need labeled malware data. VirusTotal is the largest online anti-malware scanning service. After user submits a suspicious file to VirusTotal, VirusTotal applies more than 70 engines to analyze the file and returns the engine's detection results back to the user. VirusTotal is widely used by researchers in the security community to label their malware datasets. There are three major challenges of using VirusTotal. First, VirusTotal keeps updating its engines, and the file's labels are likely to change over time. When can we trust VirusTotal labels? Second, different engines often disagree with each other. How should we resolve the disparity between engines and decide an aggregate label? Third, should we treat all the VirusTotal engines equally? We first conducted a paper survey to understand how previous researchers handle the three challenges. Our survey is based on 115 top-tier conference papers. We have three findings. First, most papers do not consider the possible label changes on VirusTotal. Second, a large portion of papers choose a threshold-based method to aggregate labels from different engines. When researchers choose T as a threshold, they will consider a file is malicious if T or more than T engines detect the file as malicious. Third, in most papers, researchers believe different engines are equally trustworthy, and only in a few papers, the authors handpicked a small set of reputable engines. We then conducted a measurement to validate the approaches taken by the previous researchers. We collected VirusTotal data for both PE and APK files. For each file type, we have a small dataset with ground truth labels and a large dataset without ground truth labels. Our measurement is launched from three aspects corresponding to the three challenges. First, we studied the impact of label changes. Second, we examine how threshold-based label aggregation works. Third, we measure the correlation between VirusTotal engines and inspect whether they can be equally treated. Due to the time limit, I will focus on the large PE dataset. We call it the main dataset. Let's first see how we construct the main dataset. We use fresh files to build the main dataset to avoid the influence of earlier VirusTotal histories on the files. We randomly sampled more than 14,000 files that were submitted to VirusTotal for the first time on August 31, 2018. About half of them were labeled as benign by all engines on that day. For the rest, at least one engine believed they are malicious. We collected their VirusTotal daily detection results over 1 year. We used the rescan API to force VirusTotal engines to analyze the files every day. We then used the report API to query the latest scanning results every day. We successfully collected VirusTotal labels on 378 days. After removing some engines with too few results, we have more than 300 million data points from 65 engines for our measurement. Next, I will discuss the impact of label changes. We model the label dynamics by sequences of 0 and 1. 0 means benign and 1 means malicious. For instance, these detection results can be represented like this. We use flip to refer to a change between two consecutive labels, namely 0 to 1 or 1 to 0. There are two possible patterns for flip. A temporary change lasting 1 day, we call it a hazard flip. A change lasts at least 2 days, we call it a non-hazard flip. This figure shows how flips change over time. The blue line represents the number of hazard flips in each week, and the red line represents all flips. There is no obvious change over time. The second figure shows the CDF of engines on the number of flips. All except one engine generate flips. However, the red line is skewed to the left, indicating that a small group of engines contributes the majority of the flips. We have similar observations on hazard flips. The third figure shows how flips and hazard flips distribute across files. We find that only 9% of the files have no flip, and about 50% of the files have a few flips. In sum, both flips and hazard flips widely exist across scan dates, engines, and files. As flips widely exist, users would ask how long they should wait until a file's labels become stable. Here, stable means all engines' labels won't change anymore. We measured the percentage of stable files as time went by. This sudden jump is because one engine has hazards on more than 3,000 files on that day. We found that only when the days to wait is more than 300, the percentage begins to increase. Unfortunately, this is because the time period between the date and the end of data collection is too small. Thus, we need to ignore this part. Even when we remove some engines with the most flips and only have 20 to 35 engines left, waiting for a longer period of time still does not guarantee to have more stable files. Next, we take a look at how threshold-based label aggregation works. As we discussed earlier, many researchers use a threshold to aggregate labels of different VirusTotal engines. When T is chosen as the threshold, a file is considered to be malicious when T or more than T engines detect the file as malicious. Here is an example. Assume we choose T to be 2. On day 1, there are 2 engines detecting the file. The aggregate label is malicious. Since VirusTotal engines may change their labeling decisions, the aggregated label may also change over time. On day 4, only one engine detects the file. The aggregated label becomes benign. We consider a file with both benign and malicious aggregated labels as a file whose aggregated label is influenced by flips. We measured the percentage of influenced files for different T. Here are the results. The first bar shows how files only with benign aggregate labels, files with both benign and malicious aggregate labels, and files only with malicious aggregated labels distribute. When T is equal to 1, a large portion of files' aggregated labels are influenced by flips. However, when T is equal to 2, the number of influenced files significantly decreases. When T is in the range from 2 to 20, the ratio of influenced file is less than 4%. When T is large, the ratio of influenced files becomes large again. In sum, flips can heavily influence labeling aggregation results when T is too small or too large. When T is from a reasonable range, the aggregate labels are likely to be stable. Now we are going to study whether engines are independent by inspecting how similar their detection results are. We take 2 steps to compute the similarity between engine A and engine B. We first compute the similarity for each pair of labeling sequences when the 2 engines analyze the same file. We then compute the engine similarity and the average sequence level similarity over all the files. Here is one example for how to compute sequence level similarity. For each sequence, we first divide it into bins. We then extract 4 features from each bin, based on the number of 0 to 1 or 1 to 0 flips and the number of longest consecutive sequences of 1 or 0. We combine features from different bins into a feature vector. The similarity between the 2 sequences is the cosine similarity between the 2 feature vectors. We visualize the similarity results using a dendrogram where x-axis represents different engines and y-axis represents engine distance. Distance is computed as 1 minus the similarity. Engines with minimal distances are connected. Overall, detection results are similar for all engines. When selecting the distance threshold as 0.01, we find several interesting clusters. First, Avast and AVG combined into one company in 2016, and their detection results are very similar. Second, these two are products from the same company Key7. Third, these 6 engines are also very similar, but they are not obviously connected with each other. Here is a file. We can see that 5 of the 6 engines reported exactly the same results. To sum up, there are groups of engines whose labeling decisions have strong correlations. Now we briefly discuss the results on the ground truth dataset. We mainly use obfuscation to create fresh ground truth samples. However, we found that obfuscation brings many false positives even for some high reputation engines. We also found that when threshold T is chosen from 3 to 15, we can have accurate aggregation labels. We noticed that inconsistency exists between the desktop version and the VirusTotal version. More results on the ground truth dataset can be found in our paper. Let me conclude my talk. In this paper, we first surveyed how previous researchers use VirusTotal. We then took data-driven methods to validate the previous methodologies. Here, we have several suggestions on how to use VirusTotal. First, VirusTotal data needs to be pre-processed, such as removing hazards. Second, a suitable T needs to be selected to aggregate labels of different engines. Third, both correlation and causality exist between engines. Different engines should not be treated equally. In the end, high reputation engines are not always accurate. Attention is still needed for their detection results. That's it. Thank you very much. I would like to take questions.